Great, thank you. Thanks for having me and sticking around this morning. So I've enjoyed the workshop a lot and I've learned a lot. So like many people, I had to look up what metacognition is. So that's the perspective I'm coming from. I'm a computer scientist and engineer. And broadly, I work on verification and formal methods in autonomy and machine learning recently. So my title has a lot of words. So as one does, I asked ChatGPT to explain it a little bit. So I mean, being a little bit silly, but it did an okay job, I think. So my kind of perspective on the metacognition side is sort of self-reflection and thinking about things and error correction and detection, which kind of came up, I think, in Paulo's talks and a couple of the other talks. So CPS are kind of modern embedded systems, increasingly incorporating autonomy. Neural network verification. I think this one is a little bit wrong. I think a lot of the work in this domain is focused on kind of perception correctness, not just decision making, which I think is a big problem. The repair piece, kind of focusing on how could we modify things and relearn to fix errors, and I'm going to define this a bit more. And then kind of another piece from what I did my initial background reading on metacognition, sort of the ability to monitor, self-monitor, realize when a mistake is made, and kind of then dig into why and how you might fix that. And that's kind of the perspective I'm going to go with. So also just for fun, I asked Dolly to explain what the relationship between metacognition and formal verification is. And this is what it gave me back. So a lot of the applications of formal verification, and I'll go pretty quickly, but I'll give you a little bit of background in case you're not aware, is in semiconductor design and digital logic design. That's the main impact area that model checking and formal verification has had, and that's in the design process. So I guess Dolly figured that out maybe. So I'm okay with the chip there, and then the kind of mind and self-awareness part. Okay, so let's dig a little bit more in and kind of give you my perspective, because we'll probably, some of us, it's been a good week so far, but it's been a long week, and we'll probably start to phase out a little bit as I go on. But so metacognition, my perspective, and what I'm going with is as we're learning and operating, kind of involves correcting mistakes and understanding and explaining why they occurred. And in formal verification, one of the things, kind of the high-level problem we try to solve is we try to prove that a property is satisfied by a system. All right, that's the high-level goal. So it's very abstract, actually. It could be anything. It could be a neural network. Could be a program. Could be a digital logic circuit. Could be a control system. Could be pretty much anything. So if we fail to do that, though, especially with the automated verification methods, which is the type of work we focus on, you can get a counterexample. And in particular, for most systems, if they kind of operate over time, you get a counterexample trace. And what this is a witness of how and why the system violated the specification. So typically, this would go into the engineering design process. If you're in, let's say, in semiconductor design, you'd use this to then go either refine your specification or your model until you get rid of that. Now, there's a lot of challenges and other aspects in that, but that's the high-level idea. The engineer would go back, use that, and refine something. It could be a real bug. It could be a spurious counterexample. Due to the way these methods work, it might not really be a problem. Okay, it could have been an issue in the analysis method. So that's kind of my perspective, and the idea I'm kind of going with this talk and the high level, as we zone out in a minute or two perhaps, the overarching idea is that the counterexamples are mistakes, these counterexample traces, and then we can use counterexamples as a way to improve learning. And if you were here for like Ufuk or Swarat's talk or Lindley's talk, these ideas kind of came up. But I have the benefit of going after them, and I've synthesized a little bit of at least my perspective on some of what's going on. Okay, so a little more detail on my talk title, just to give you a little bit more on kind of how I thought about it instead of ChatGPT, and I'll tell you a little bit about what's going on. So on the verification side, a lot of the work we've been doing the past few years is in component level verification. So we verify neural networks. What does that mean? It's kind of a burgeoning field. We've heard some about it at this workshop, but I'll tell you more. I'll tell you a little bit more about verifying closed-loop systems that use neural networks as controllers. So that's been one of the focuses of our work. There's a lot of background, so I have way too many slides. I'm going to skip some details, but I can kind of jump into some if there's interest. So then on the repair side, there's a kind of subfield in formal methods for machine learning and whatnot working on repair. There's program repair, there's neural network repair, there's all this. And the idea would be to use the counterexamples to improve learning. So perhaps retrain neural networks, maybe broader systems, until they can verifiably satisfy those specifications. So that's how we would kind of use this. And I'm going to give you a few more details in case you don't have too much background. And then the monitoring side would be predicting if specifications will be violated in the future. So this doesn't always make sense depending what the problem domain is, right? For image classification, maybe this doesn't totally make sense unless we're using it online in a system. So this typically in like an autonomous system, something that's running, so I'm thinking of robots and things like this, this would be kind of like predicting what may happen in the future up to some finite time horizon, and then avoid a specification violation if it's possible. Okay, so good. Just show of hands, who knows much about formal methods? We'll keep it a little bit interactive. I see one hand. Okay, so 2 hands, okay, maybe. A few hands, okay. So I'll give you, let me give you a little introduction, okay? I don't want to insult anyone, of course, if you have some background, but let me define a few things and just give you a little bit of background. So we use different languages to formalize things in formal verification. Often we use temporal logics. So LTL, or linear temporal logics, is one of the common logics. So what this specification here says, so this says it's always the case, so G is globally or always. If some predicate P holds, then eventually in the future Q holds. All right, so this is an example of a kind of liveness type specification. All right, so what's a trace? So a trace is just a sequence of these predicates. All right, so each of these P's and Q's, you can think of these like Boolean propositions. All right, so it's just a true or false. Something holds, something doesn't hold. So this would be a satisfying trace. So what should this tell us? These sequences, by the way, so these are finite representations, these could be infinitely long. And in classical verification, we often do care about these infinite behaviors. So what this would say is that if I see a P, then I need to, at some point beyond that on the trace, on this sequence, see a Q, right? So I have P's satisfying, and then I have a Q, so I have some P's, then I should find a Q, right? So that's the basic idea. So what would violate this? So an example that would violate this would be if I just see P forever, right? So that would be an example. So P held, so it was the case that P held, but then in the future, it was never eventually the case that Q held, right? So this would violate it. This would actually, violating this and can come up in classical verification like this, could require such an infinite execution or an infinite trace, right? So what this means, this would be like this could illustrate a kind of live lock scenario or a deadlock scenario would be what this would kind of illustrate. So this is one class. So now these are instances, but there are actually infinitely many satisfying traces, right? So what would all these look like? Well, you know, what are the distances between the P and the Q? So, okay, so this one I have some P's holding, then Q, some P's holding, then Q. This one I have a P, then a Q, maybe another Q, that's fine, but then I have a P again, then followed by Q's, all this, all right? So there's many of these. Any questions? Some background, kind of makes sense? Okay, all right. So of course we could teach a whole course on this, and we do that, many courses actually. So this, I'll just give you what are properties and how does this relate to systems and traces. So this kind of builds on old work. This is kind of the topological perspective in formal verification. This is like the Fred Schneider type approach and a lot of interesting work like this. So I have this trace, so it's a sequence, right? So I previously defined it in terms of predicates, that's fine, but I can think of this as sequences of states as well. And then the predicates would just be some Boolean constraint over that, over the states of the system. So a property would be a set of possibly infinitely long traces. Then a trace would satisfy a property if and only if the trace is an element of some set of traces P. So it just depends on the trace. Then the system we also represent as a set of traces. So these points, these are sets of traces. So these are sets of these sequences. Okay? Then essentially what we're saying is a system satisfies this, and there's all kind of background, and this is provable. We'd say that the system satisfies the property P if and only if all the traces of the system satisfy that property. So this is what it would look like. So kind of high-level picture here that I'm trying to get across, and again, this is the classic kind of stuff in finite state machine type background. So our system would be a finite state machine, our property is some temporal logic specification. this is how we'd kind of do it. And what you can see, I'm kind of looking at some set inclusions, and this type of thing commonly comes up. Okay, so we need to be able to compute things like this and then compare sets to one another. So those will be common operations. Okay, so if you zone out now, it's okay, but I'll tell you a lot more details. I'll tell you how this ties into neural networks. I also want to thank all the group members in my group. So I won't talk about everyone's work, but of course I got to be here talking with you all, and we know who really does all the real work. So a lot of the work I'll talk about, I'll start with some of Patrick's work and talk some about Wei-Ming and Tran's work. Patrick's at Google now, and then Wei-Ming and Tran are both faculty. And I may get to talk a little bit about Xiaodong's work, but I'm already like 10 minutes in, so I'm probably, we'll see how it goes. Okay, so it'll be a choose your own presentation style presentation based on if I see everyone falling asleep or not. Okay, so I want to thank them. So what's some of our motivation? So our motivation is autonomous CPS. So there's a lot of applications to this. This is an illustration in our lab of F1/10th cars. These are 1/10th scale formula racing cars, popular kind of test bed used in the community. So they're representative of autonomous systems. So they have LiDAR. They have neural networks that are processing things. There's real-time aspects. We're running this on hardware on the car. Okay, and we may look at like collision avoidance or something like this, right? So kind of stopping, seeing what's happening, those type of things. So just as you'd kind of expect. Okay, so this video is pretty good. I won't play the whole thing. So it looks like it's working. The F1/10th cars, by the way, the high-level problem is to do racing. Okay, so you'd have a couple of these. There's simulation-based versions of all this as well, but they'd race. So it's a nice platform. It's fun. There's a great competition that's held with robotics conferences like ICRA, IROS, and sometimes the CPS venues like CPS Week and so on. So we've done some other things for this. We're doing monitoring. So we have a couple of these. This is just showing another scenario. So, and this is an illustration. I'll talk a little bit about monitoring, and I'll show you one thing we've done there. So this is computing sets of reachable states online, and I'll tell you a little bit more about this. But basically the idea is we are forward in time predicting the positions of where the vehicles could be. And according to a model, in this case some differential equation model, up to some finite time horizon while following control actions produced, in this case by a neural network controller. So trained, we've got several variants, but some were imitation learning trained, some were reinforcement learning trained. But basically predicting we will not collide. And that would be collision with the other vehicle, also collision with the environment. Okay, and I'll tell you a little bit more about that in a second. So those are nice looking videos. So of course, if you've done any robotic stuff, things don't always go so well. And I want to tie this particular instance. This is a common scenario that shows up in the real world. It's also a common scenario if you go back to like DARPA Urban Grand Challenges and things like this that commonly occurred. And this actually is an illustration of a violation of that specification I started with. This is a live lock. This vehicle forever, I mean, it'll run out of battery eventually, okay, fine. But it's always going to be going back and forth. So this violates that type of specification I wanted earlier. Right? That always, it's eventually the case that something happens. And the predicates I could have there maybe would be, okay, I want the position of the vehicle. It's always the case that if I start at this line, then eventually I come back to this line, something like that. Okay, so that at a high level, this would kind of be an illustration of that kind of violation. Okay. Right, so lots of other great instances. I won't tell you all the details about these, but we've looked at, that was a ground vehicle scenario. We've also looked with AFRL at space and air vehicle scenarios, and this is some of Preston's work. And we did a lot of this work with Karen Hobbs at AFRL in Dayton, along with other folks, and Nate's now a research scientist in Dayton at Parallax. So this is a spacecraft docking scenario. These are benchmarks people develop in this community for evaluating algorithms, evaluating safe reinforcement learning and things like this. All right, so what's the setup here? So we could motivational, what classes of systems are we looking at? So we'd have some dynamics for these vehicles. We'd also have a controller for this, in this case controlled or trained with reinforcement learning. So there's another air vehicle scenario doing rejoin maneuvers using Dubbin's ODE type dynamics. And we have a variety of different specifications that would come into play here. So safety type specs, we don't want these things to collide, and we do eventually want something good to happen. And broadly, a lot of specifications fall into these classes. Okay. So I'll tell you a little bit about, so we participated in the shared autonomy program with DARPA, and one of the platform providers for this was Northrop, who we were paired with, and we're developing an autonomous underwater vehicle. This is kind of one of the use cases and challenge scenarios, and I'll tell you a little bit about this, and I'll tie in some of the presentation into this framework. So the high level of goal of this was to develop assurance and verification methods in the context of these kind of autonomous CPS, particularly learning-enabled CPS. All right, so we have machine learning components in them. I'll sometimes maybe call these LECs or learning-enabled components. And so my group, we had a team at Vanderbilt, and it's a little bit broader than this, and I'll tell you some about it, but we focused on verification. So one specific challenge problem in this, which is kind of getting onto the component level, is doing robustness verification for computer vision problems like semantic segmentation. So in this vehicle has a side scan sonar, which is used to identify a pipe or a cable. This is just a deadband. This is not the pipe or cable. This is where the cable is. And then semantic segmentation was applied on this. This is sonar data, but basically this is just this is an image after it's acquired, right? And they actually just use typical CNNs were used for this. So kind of VGG and then SegNet type architecture. And the output of this is basically what pixels correspond to that pipe. Then you'd fit a line to this, and then this would feed into a higher level controller, right? So this would kind of feed into, we want to follow that cable or follow that pipe with the underwater vehicle. Okay, so this is again representative. I'll just have an architectural picture briefly of what kind of the autonomous CPS architecture could look like for this. So this is not exactly, that previous slide had an IVER underwater vehicle. We also had our own internal one at Vanderbilt for testing purposes, which is a Blue ROV. We have an overall kind of autonomy stack for this. And an overall control system, so at different kind of different modules here, but just kind of illustrating the overall kind of closed loop setup that we would have for these type of systems, and this is just a representative architecture. In this case, what we're controlling are thrusters on the vehicle, so spinning with different motors that are turning propellers and so on. So then we have sensing, we have perception. So perception would be like the semantic segmentation I just talked about. We also have planning, so where do we want to go? And then also we have control and actuation and all of this. And then we have at a kind of higher level some of the autonomy management stuff where we'd be monitoring things, maybe using some of this online monitoring that I'll talk a little bit more about. Okay, so I won't go through all the details, but kind of the high level type of architecture we can imagine. So I'm going to spend a little bit of time talking about an abstraction of that's simplified, but is representative as well of some of the scenarios that I began with. So some of the RL type scenarios. So there's an old area of control theory now, actually. In the 90s was very popular intelligent control theory, but we're calling these neural network control systems now. And basically what the setup here is I have a plant model, so typical kind of differential equation model of this. And then my controller is a neural network. And using observations of the plant, so we observe the system states, we feed that into the neural network, and then come up with new control commands. And we may want to do verification for these classes of systems. So I'm going to tell you a little bit about that. I'm going to, of course, have to skip all kind of details and background. But what you can imagine doing is you can just imagine, one thing you could do is just an initial value type problem, right? So from an initial state, what are the trajectories, what are the behaviors of this kind of system? So one of the approaches for that type of systems, and I'll talk a little bit about, is with our neural network verification tool, NNV. So I'll tell you a little bit about this. There's all kind of details on how we model the systems. So we often use hybrid automata, which if you're not familiar with, these are just like finite state automata, except extended with sets of real valued variables, where those real valued variables can evolve according to some differential equations, in more general cases, differential occlusions. over some intervals of time. So basically, you can have switching behaviors in the differential equations. And there's all kind of formats to actually make all this work, and so on and so forth, and a lot of background. I won't go through all of it. But basically, then we'd have neural networks that are the controllers, and that's kind of the setup. And we've looked primarily at safety properties for these. So these wouldn't be as general as those temporal type properties that I began with. This would just be like something bad never happens. So you don't run into a wall. You don't run into the other vehicle. That's it. And these typically are going to be finite time. In the finite state automata case, this gets a little bit more complicated. Okay, so let me give you kind of a cartoon representation of what some of this looks like and make a little bit of those concepts more clear. So this is the type of thing we can do. And this broadly is how you do verification of safety properties. So we'd say that a system is safe, so it satisfies a safety property, if the intersection of an over-approximation of a set of reachable states, which I'll define in a second, with some unsafe states is empty. And this is commonly what's done. So let's say I have a set of initial states and I have a set of unsafe states. So those traces I talked about for these type of systems, so I started off in kind of the classical finite state automata world. In this case, the trace, just think of this like a trajectory. It's a solution of that differential equation. Okay, so in the kind of case we're looking at here. And in here, this would be like the control input. Some details get important, like you're actually updating the control input as a function of the state and so on. But that's the basic idea. So what is kind of a trace of that? So it's like this. So it's a solution, a trajectory of the differential equation. So from that set of initial states, there's non-determinism here. We have then sets of traces. So all these traces should be contained in some set of reachable states. All right, so this would be all of the possible states we could get to in the state space from any point in this initial state by following some differential equation. And you can add non-determinism in various places, in the differential equation itself, and in the control, and different things. What this tells us, because all the traces are contained in this set of reachable states, is that if it's safe, then there can be no counterexample like this. There cannot be a trace that takes us from initial states to unsafe states. And this is the high-level idea of what's done in safety verification. So now there's a challenge. There are a lot of challenges. So this problem is undecidable. So that's tricky. So this problem is undecidable for interesting classes of differential equations, I'll say. Many subclasses, their decidability results in various things. But one thing that means is that we can't actually fully solve that problem. We often over-approximate. So we do something that's sound, but we may not be able to give a definitive answer. We may come back with unknown, right? We may say, maybe it's safe, maybe it's not. So if this over-approximation, and the over-approximation of the reachable states is just another set that contains all of the reachable states, that set, if that set doesn't intersect with the unsafe states, then we're good. If it did, then we could have what's called a spurious counterexample. And that would just be a case where, due to the way we've done the over-approximation, if this kind of set, right, so if this kind of overlapped here, the actual reachable states didn't intersect with the unsafe states, but there could have been a portion of that over-approximation that did, right? And that could be like an unknown. Okay, so that's kind of the high-level idea, and that arises in part due to the decidability and also to make this stuff scale. So in the analyses, we always want to be as imprecise as we possibly can. Otherwise, we're not going to be able to scale. And that's one of the ways that we address scalability in applying automated verification methods. Okay, so what could this look like in a couple of the scenarios I mentioned? So in some of Patrick's work, we did runtime monitoring and verification for these kind of systems and I showed you in the video a picture of this, and I'll show you a couple more videos, try to keep it a little bit engaging. It's a little early to be talking about formal methods, perhaps. But we have some algorithms we've developed where we can do reachability with real-time guarantees. And what I mean by real-time here, I mean real-time in the real-time system sense. So these algorithms come with worst-case execution time guarantees, WSEC guarantees. So they can be deployed on hardware, and we've done that. And this is important in real systems, right? So the basic idea here is you just think of this like a set valued simulation. So this would be like one trajectory, so like one initial value problem being solved. And now imagine I've bloated that. Now, the details of this get important. How do you do that soundly, such that I have a guarantee that these traces are contained in these other sets, okay? But we do this online, and we use an old method to do this that's called mixed facelifting. This, a couple of years ago, won the Test of Time Award. This is not our work, but based on the work of Tao Deng and Oded Mahler, that won the Test of Time Award at HSEC, which is one of the formal methods and verification conferences, particularly for these type of systems. And our observation to do this online is that over a small time horizon, so let's say after we've come up with our control value, we need to just predict where we're going to be, right, over a small time horizon. So the reason people don't use this kind of algorithm anymore is this uses a state space representation of rectangles, hyperrectangles in high dimensions, and this gets very imprecise. So if I were doing offline analysis, you'd no longer use this. But if I'm doing online analysis, this is fine. And the observation is with that fixed control input over some small time horizon in the future, I can predict where the vehicle will be. All right, with guarantees, you can incorporate uncertainties like noise and all sorts of stuff. Okay, and the background of all this is in these papers, and I'll show you a video of what this looks like. So this is in the AUV scenario. These lines, these are waypoints. This is the pipe. There's obstacles that'll dynamically appear. There's a forward-looking sonar. We've incorporated failures in these scenarios. And we're trying to avoid collision with these dynamically appearing obstacles. And this kind of little red piece in the front now, this is the set of reachable states up to some small time horizon in the future. And you can see as the vehicle would be kind of turning a bit. Now we're going to go back and kind of follow some of the pipe. As this vehicle would be turning a bit, this is really predicting up to, say, 3 seconds in the future, where could that vehicle be? Incorporating environmental uncertainty, so some uncertainty quantification here. So this in this kind of scenario, it could be from noise, it could be from actual environmental disturbances. So this is underwater, there's not waves, but there's currents, right? The vehicle's moving around, and all sorts of stuff. Okay, so I think in the interest of time, I'll skip this because I want to get to a few more things. So I think, how much more time do I have? 13 minutes, okay. So I'll tell you a few details. I'll skip a bunch of stuff. I think, people had a little bit of background in formal verification. I told you a little bit about this. I think I'm going to skip a little bit of this. I'll mention all of our tool chain is set up with a variety of other things with out-of-distribution detection and all this. This is kind of the overall tool chain that was developed in our Assured Autonomy project. It's all available online. Our verification tools are all online as well. And this is kind of the overall setup. So there's a lot broader things from doing modeling and training and integration with all these simulators, deployment to hardware platforms and all that. Okay, so let me talk a little bit about the perception challenge and robustness verification and tell you a little bit of details about that. So we've seen motivation with adversarial perturbations and things like this. In autonomous systems, these of course could have real world type consequences. So this is kind of a famous, at this point, illustration of a physical adversarial perturbation. So this graffiti is added to a stop sign, and then it's shown that typical image classifiers for these kind of signs classify this as a speed limit sign. So if you're using this information in a closed loop system to decide whether to stop or to go, what's going to happen? Well, this is bad, right? The vehicle is going to go straight through that stop sign, so that's not good. So how can we address those kind of things? So there's all kind of other illustrations of this, but in the interest of time, I'm gonna kind of like move along. So one way to do that is using methods like what we've developed in our NNV software tool. And I'll get into a little bit of how this works and just define this problem concretely. You've heard some about these type of methods already at this venue from like Lindley yesterday and Swat a little bit yesterday. But I'll tell you a little bit more about it. And this is just all the background of this. So we'd like to have different classes of models, so different ones I've talked about. So things like the neural network. And then I may want to show that, for example, that kind of adversarial perturbation cannot occur. This, of course, is under some assumptions. I may have that neural network control system, and I may want to show that, for example, we don't have collisions. And these at the high level would be the type of things we want to do. So the newest version of this, we have a new version that supports a lot more model types than just these. neural ODEs, different classes of differential equations, nonlinear, linear, hybrid systems, RNNs. We've just been expanding the model types, essentially. So there's a new version of this that was presented at CAV this year. Okay, so what do we do? How do we do this for neural networks? So I need to take one step back. A lot of the things I was talking about were temporal things, right? So we're going to take a step back now, and I just have a neural network. So let's just suppose, what is an abstraction of a neural network? Well, it's just a function. It takes inputs from some space R to the n and produces outputs in some space R to the n. So then what essentially all of the neural network verification methods are doing, that at least are doing this kind of worst case analysis, I'm getting rid of all the temporal stuff, so forget all that for a second. What we call this the output reachable set, but essentially what we're doing, we need to compute the image or the range of that function representing the neural network under a set of inputs, and that's what we're doing. So this set of inputs could represent adversarial perturbations up to some epsilon away, right, under some norm. And that would be like the tie-in. I'll show you what that looks like. So we then need to push this. We have this set, and then I want to know where could I go. So we need to compute this image or the range of that neural network under that set of inputs x. And then we'd go back to this kind of typical thing I told you a little bit about. We need to check intersections. So the overall problem formulation here is the intersection between wherever we could go from some set of inputs with some specification in the output space, is that intersection empty or not? And that's the overall problem. And that's what, there's all different methods to do this. What we do computationally, we essentially propagate polytopes through the network, layer by layer. So I'll mention just a little bit about how this works to give you some intuition. And then we'd check set intersections of these things. Okay, so what does this look like? I'll just give you a kind of a toy numerical example just to make all of this hopefully very concrete, and then I'll try to link it back to adversarial perturbations. So we have that neural network. In this case, let's say it's a toy network. So it maps from R3 to R2. Okay, so 3 input neurons, 2 output neurons. And let's say internally it has 7 hidden layers with 7 neurons each. This, again, is a toy. In the community, you can scale to realistic networks. So we've analyzed VGG, ResNets, other things, okay? But this is just for conceptual purpose. Let's suppose our input set, X, so this is our subset of the initial state space, so a subset of R3. Let's say it's this cube. I push that cube through the network, and then I get a set of outputs. Now, computationally, what's happening internally is we are transforming that set. Now, if we have things like ReLU activations, which are piecewise affine, all of these transformations are essentially affine transformations, so they're translations, rotation, scaling. And with the ReLU activations, we then may also need to split sets up. So that's just the intuition, but it's just going to like zero some things out. So it'll just be a projection down, essentially, into some lower space. So pictorially, what this looks like from this cube, this shape, this is the union of all the different shapes here. That is the exact set of reachable states for this neural network. So what that means is if I take any point from in this cube and I just do inference, so I just apply that point to the network, so I just do evaluation or inference with that point, it is contained in this set. And you can see that here when we just take 8,000 random points from inside that cube. You can see that all those points, it's maybe a little hard to see, but these are just where we could go under that network, right? So these are the inferences under that. Okay, so this is kind of an empirical soundness check that this makes sense. And then what we could do, I mean, this doesn't mean anything for this toy, but we would then check, is there any intersection, non-empty intersection between these two sets, yes or no? You can do fancier things like distances and all sorts of stuff, but at a high level. So there's all kind of interesting scalability challenges. This problem's NP complete. For other activations, it gets tricky if you have transcendental functions like tanh and various things. But the intuition of this, as you go through the ReLUs, again, assuming all activations are ReLUs just for the purpose of this example, you may need to split things up. So here we started with one shape, and we ended up with 1,250, all right, through this kind of toy network. So scalability is a big issue. So you have to do abstraction and various tricks. Okay, so I have a lot more. I'll skip over the ReLU stuff, and I'll, in the next minute or two, try to wrap up so we can have a little bit of time for questions. So how does this tie into adversarial perturbations? So let me just make that link to you clear. So for MNIST, and this is now old, so things again scale up, we do the exact same thing. And now what you do is you take a test data, so you take a test image, and then you consider nearby images. So for example, under the L infinity norm up to some epsilon distance away, what are all of the nearby images? And then now that's the set we send through. So we need to represent that as a polytope, but how does it scale up? So one of the challenges here, if I look before actually doing the classification, typically in this, we'd get these kind of scores or whatever, and then we take the argmax or the softmax, and that would be the class. So for a 0, right, I can say, okay, this image was a 0, predicted as a 0, and that would have been the highest score. So now essentially what we'd have, this is a projection down. We've actually done the computation from r to the 28 to r to the 10, and what we're visualizing here now is just the projection down onto the 10 MNIST classes, right, under the 10 digits. So we now get intervals here under that projection. So we projected that 10D shape down along each of the 10 classes. All right, so basically at a high level what this is going to look like, we're going to have these intervals. So if the lower bound of this is greater than the upper bound of any other class, then we'd say that was robustly classified under whatever the perturbation was. All right, so that's a high level, and that's what most of the methods do, and there's lots more details, but the high level. Right, so I mentioned a little bit on some of the new features. So semantic segmentation is one thing. There's RNNs, broader classes of neural networks, neural ODEs, and various things. And I'm going to skip over related work. I'll mention there's a great competition. I say great, we co-organize it with other folks, called VNN-Comp. In the verification community, people often, to evaluate scalability, work in competitions. So there's one for neural network verification called VNN-Comp. We've participated, as have many other people. There's also a hybrid system verification competition and a special category on neural network control systems called AI NNCS that we also help co-organize and has been running for a while. So these are good kind of starting point references. Okay, so I'm almost out of time. I will tell you we can scale up to larger things, but I want to kind of get to some conclusions. We have done this in these segmentation scenarios with different things, including the AUV scenario. So basically, we looked at adversarial perturbations, applied in inputs there, and we've generalized this to semantic segmentation. But basically, if you think about classification now, I just do classification at every point. So how do we use this? So we can use this to prove properties hold for neural networks in terms of input-output specs. And we can also use this, again, a lot of background on how all this works, but we can also prove properties hold for neural network control systems. So that kind of class of autonomous CPS I talked about. So how do you use this? You saw this in Lin Li's talk already, but you can use this to characterize like certified accuracy. So there's metrics that were given there, and what is the certified accuracy or certified robustness? This is a piece in doing that kind of computation, right? So this is how those numbers would be come up with. What percentage of that test data set could you show was robust? Now, due to abstraction, you may get unknowns, and there's all kind of interesting challenges, but that's why that certified accuracy can't go all the way up to the actual accuracy. There's great benchmarks being developed in the community and other autonomous CPS. I'll mention this Collins remaining useful life benchmark for prediction. This could show up in monitoring. This is a VNN-Comp benchmark. I'm happy to talk more about it. And I think I'll not have too much time to talk about repair, but we have looked at this in the context of retraining and using the specification violations to go back and fix things. And there's another tool we have in this paper at Formats last year is one of the works we did on this. And the basic idea, you get to an image that I have. The basic idea is we would see how we violate the specification and see what subset of input points for a neural network caused us to violate that spec. And then you can use this to modify a loss and go back and retrain things. Okay, so a few conclusions, and I'll tie back to the workshop theme. So I gave you an overview of NNV, some of the autonomous CPS things we do, our broader tool chain that was developed in assured autonomy, and continuing to be developed in Answer, with also Neuro Symbolic components. So a lot of vibrant research community here. So the VNN competition, the ARCH competition I mentioned, and I kind of put all this, I'm coming from formal methods and verification, but I put it kind of broadly in the kind of overall trustworthy AI community. So it's a few details on VNN comp and some links to reports. There's another workshop people may be interested in from last year that Jerry Hsu and Kate Cinco and I co-organized, and Dr. Kathleen Fisher spoke, as did Deb Raji, kind of looking at similar types of issues, not with this metacognitive theme, but kind of broader safety and trust type considerations. Okay, so I'll conclude with coming back to my perspective and the overarching idea. Lots of other interesting work on other application domains and all sorts of things. So the perspective I'm coming from with formal methods and verification here is that counterexamples to specifications are the mistakes or errors, and we want to use those to go back to improve learning, which, at least from my very high-level engineering understanding of what metacognition might be, may be a kind of reasonable conceptual tie-in. Okay, so I thank the group again. Thank you all for sticking around. Thank all of our sponsors, and I'll open if we have any time for any quick questions or anything.